Okay, hi everyone. Welcome back to the Topos Institute Colloquium. Today we are very honored and pleased to have Brandon Shapiro, and he's going to be talking to us about higher categories in Cat Sharp. Very excited to hear this talk. Whenever you're ready, Brandon. Thank you.
All right. Thanks so much, Xiaowei, and everybody at Topos for having me back. So, as you see on the title slide, I'm at the University of Virginia now, but the bulk of what I'm going to talk about today was conducted at the Topos Institute. So, very nice to be back and talking about this stuff again. So, the main topic is going to be on higher categories and how we use this polynomial functors formalism, in particular cat sharp, which is a major player in that, uh, to do a lot of stuff in higher categories. So that's the idea. And by higher categories, I'm going to mean things that are algebraic, like two categories and double categories, not whatever your homotopy theorist friends call infinity categories or infinity one categories, though there are connections. So what do I mean by higher categories more specifically? Well, higher categories is meant to be, in my view, a generalization of categories. So it makes sense that it would also include categories themselves. And the feature which we're going to generalize when I talk about these things is what are the cell shapes? So for categories, we've got our dots, which we sometimes call objects, and our arrows, which we sometimes call morphisms. And we have all these ways of composing them. And we have equations between those, like the second diagram down here kind of indicates associativity. If we have three successive arrows, we can compose them in a unique way, regardless of whether you compose two of them first before all three. And we also have identities, so that's the point. And what was that? Okay, sorry about that. And so another type of higher category, which is probably relatively familiar, is two categories, where we have the same shapes, but we also add these higher dimensional cells called two cells. And we can compose them in all sorts of different ways. Vertical, like the columns in these diagrams, horizontal, so along one of these dots in between two cells, we can compose them that way. And I'll show you a more visceral picture of this in just a minute. And we can also get fancier combinations where you compose sort of any sequence horizontally of these sort of vertical stacks of two cells. And these compositions are sort of closely connected to the combinatorial geometry of these cell shapes. And another relatively well-known one that I know is popular at the Topos Institute is double categories. So these are like two categories in some ways. They're two-dimensional. They have two-dimensional shapes. But we have two different types of arrows, which here I've denoted by red and blue, though there's, of course, a million different ways of doing that that are standard. And so we've got the red arrows and the blue arrows, and those are distinct from each other. So you can have, one class of red arrows and one class of blue arrows. It's entirely different. And the two-dimensional structure looks like squares that sort of commutes these different sequences of arrows past each other. Red arrows and blue arrows don't compose, but we can commute them using these squares. And the squares compose horizontally and vertically in an actually more straightforward way than two categories, because it's all in a grid. And then something a little bit different, which I really think of as one-dimensional, though you can decide for yourselves whether you agree with that through the pictures, is multi-categories, where we only have dots and sort of a variety of different kinds of arrows, each of which has one target dot and potentially many different sources. And so each of these arrows types is really a different cell shape based on how many inputs it has, and we can compose these in tree formations. And also for some people will call these operads. I think of operads as the one object multi-categories, but I won't need to get into that. So these are some different kinds of higher categories. And of course, there are many others. You can get higher dimensional, you can find different kinds of cell shapes. You can have like more complicated composition operations. Here, all the composable diagrams are kind of connected. Whereas sometimes you could compose like disjoint arrangements of things and get something like a monoidal structure. But the goal is to be able to talk about all of these things in a common language. Because in the individual theories of a lot of these, we've got a lot of similar features. Like, in categories, we've got our categories, we've got our functors between them, we've got natural transformations, these things called limits and colimits and adjoints and equivalences, Grothendieck constructions, enrichment, all these different sorts of things, many of which have analogs in two categories, double categories, multi-categories, n categories, whatever you like. And it would be neat if we could kind of come up with standard formulas that would be able to do a lot of those things. And so I'm not going to talk about too many of those today, but I will tell you that the polynomial functor formalism gives a nice way of doing at least some of these things. So to get closer to that, I'm going to make this a little more formal. So let's consider this category G1, and people go back and forth between whether the arrows point up or down. I'm going to use down because it's more convenient for the polynomial formalism. And so we've got 0 cells and 1 cells is what this is meant to indicate. And the 0 cell is like a point, the 1 cell is like an arrow, and the source and target are meant to indicate that the 1 cell has a source that is a dot and a target, which is a point. And so if we consider G1 sets, which is just functors from G1 to set, then this is the category of graphs, or rather what I think category theorists like to call the category of graphs without all the adjectives. So these can include loops, parallel edges, all that good stuff. And some people would rather define this as a contravariant functor category using G1 op. But I'm not going to do that today. So how do we get to categories from there? That's where this is going. So if we have a graph, which is a cell diagram, you could say, where the cells are points and edges like so. We get to categories using a monad on graphs. Categories are going to be algebras for that monad. And what that monad does is it takes a graph, and wherever it sees two arrows that look like they should be composable, it adds in their composite. And not just 2 arrows, also 3, 4, 5, or 0, where 0 being the identities. So I'm going to call this monad FC for free category. And monads, in particular, ones that have a similar form to this, are going to be what we use to generalize categories to these other types of structures. So this monad has a particular form. The vertices are the same. You'll notice I didn't add any vertices, and that's going to be true for any graph. And in particular, you can see then that the assignment on vertices is representable by the walking vertex, by which I mean the graph with just a single vertex and no edges. If you take natural transformations of G sets from that to X, you recover the set of vertices in X. But then for the edges, it's not quite representable. We're sending the edges in FCX are all of the finite length paths in X. And those paths are all going to look a little bit different depending on their length. But if you're willing to split up that set according to those lengths, then you can recover it as a disjoint union of representables. So in particular, the set of paths in X, which is edges in our free category, is given by the disjoint union of maps from these walking length n paths into X. So when n is 0, it's just a vertex. When n is 1, it's just an edge. When n is 2, it's these 2 successive edges that you see we've added in a composite for here in green. And so this is the form of the monads that we're going to be interested in. Ones where we can break up each component into a disjoint union of representables, where those representing diagrams are going to be the things that we know how to compose. So in this case, it's these strings of adjacent arrows, and we compose them into a single arrow which corresponds to this being in the one cell component of this monad. And of course, you get the sources and targets of these paths by sort of including the point into this graph in the front or the back. But I won't get into that detail too much. And so we get, except in this picture, where you see that each of these arity diagrams, as I'll come to call them, have a source and target vertex, which is key to the formulas we get in categories that you don't always write, that the composite has source equal to the source of the first one, and vice versa for the target. So we get this kind of setup, and we see that we can do it for other things as well. So if we upgrade this category G1 to G2 by adding in another object, which is going to represent our two-dimensional cell, it also has a source and target that are one cells. So that looks kind of like this. We've got the two cell, it's got a source and target that are one cells, and the relations in this category come from the fact that it only has these two vertex spaces as well. And so if we keep going along these lines, we get a category of two graphs by functors from this into set, where a two graph looks kind of like this. So if you ignore all the two-dimensional arrows, it's just a graph, but it also has these two cells, much like a two category, but without assuming any composition. So this is a meaningful analog of graphs. I call things like this cell diagrams. And we can sort of do this whole picture again, where we get the two categories are algebras for a monad on these two graphs. Whoops. So I'm going to call this monad F2C for free two category. And what does that look like? Well, first of all, if we just look at this top bit, we compose all of the arrows like we would in a category. So for instance, there are many different compositions in this two graph, but to highlight just a few of them, if we compose all these arrows along the top of each column, we get this green one along the top. Composing along the bottom gives us one, and you can pick any sort of combination of things in the middle, like these blue arrows. And then if we zoom out a little, so we just write those three arrows, we also get composites of the two cells. And so I've drawn those in down below, where this top one, downward pointing, is the composite of all of these downward pointing ones, including this sort of degenerate two cell, given by just this blue arrow on the right. And then this bottom one is this horizontal composite of these three upward pointing ones. And so, of course, in a more complicated two graph, we would get many more two cells. And indeed, we have more two cells here as well. You could horizontally compose this and this, this and this, vertically compose these two, etc. But the biggest ones are the ones that I've drawn in here. And this monad has a similar form, which is sort of where this generalization is motivated by. So now we've got three different components of F2C of a two graph X. So again, the vertices stay the same. And in this case, the one cells, the arrows, look exactly like they do in a category. We just take all of the paths of arrows through our two graph. But now for two cells, things get a little more complicated. Like we saw down here, we had these sort of many different types of diagrams that could compose into a two cell in the example. And so I'm sort of just going to index those. I'm going to call each of those shapes pi and show you, in this case, just one of those shapes, where we see from this picture before that not only do our composable diagrams that output one cells have source and target zero cells, but we get a whole bunch of composable diagrams, sometimes called pasting diagrams, of two cells, which are all sort of pointing the same direction and arranged into this sort of horizontal sequence of vertical columns. And all of them have source and targets as well. So their source and target one cells are going to look like just the number of arrows on the outside that you're composing on the top and bottom. And that's going to look like one of these composable diagrams for one cell. So this was when I composed all of the top arrows and all of the bottom arrows. or in this case, for the downward pointing ones, all of these top arrows and then these blue arrows, which gave us the source and target of this composite 2-set. Whoops, oh, this is supposed to be F2C. Sorry about that. And so we get this similar picture where all of the algebraic structure of a 2-category can be boiled down to what are the different kinds of compositions we can do to get a 0-cell, a 1-cell, and a 2-set. We have some number of operations. Each of those has an arity, meaning the specific diagram that you can compose into a single 2-cell. And those arities are related by this source and target information. And so this is going to be the general structure of the types of algebraic higher categories that I'm interested in and that we're going to be able to model using polynomials. So continuing the march to greater formality. So we'll keep this picture in mind and we'll start to write this down more carefully. So we're going to study what I like to call familial functors. They go by a few different names and I'll mention some of them as we go. But first of all, just what's the information that's going on here? So first of all, what are the operations? And they're going to form a functor from our category of cell shapes, let's see, into sets. And so for our free category monad on G1 sets, graphs, that functor sends 0 to the singleton set containing what I call 0, and it sends 1 to the set of natural numbers. And that's because there's a single operation on vertices, just keep a vertex that you already had, and there's natural numbers, many different operations outputting a 1-set. You could get an identity on a vertex, an arrow you started with, or composites of length n paths. And this is a functor because each of them has a source and target operation that's a 0-cell. In this case, not so interesting, but in 2 categories, we had a lot of choices for those. So then we have the arities, and the specific functoriality of these is not necessarily worth getting into. Oh, I'm so sorry. That should be the category of elements of f of 1, not this s. Apologies for that typo. But the point is that for each operation, we have an arity, which is, in this case, a graph. In general, it's going to be a diagram over the target, a diagram in the target cell shapes of our functor. So in our case, we're mostly just going to be interested in monads. So for categories, those arities are these walking paths of length n. And the functoriality statement is just saying that they have source and target vertices, which we saw before and we see in this picture. And then given that information, we have this general form for the familial functors where we send a D set X to a C set whose C cells, where little c is an object in the category big C, are given by this disjoint union of representatives, represented by these areas. And so we see in this form, if you want to build a category from, or rather, if you want to send a graph to its free category as a graph, then you take this, for edges, for instance, again, you take this disjoint union over all of the different path lengths, and you identify all of the paths of that length in X using graph homomorphisms. And if you think about how this, so I showed this a little bit for 2 categories. I could do it for double categories, multi-categories, monoidal categories, though I won't for the sake of time. You get that this general form, in particular monads, which I'll mention in a second, are a useful way of describing all of these different types of higher categories. It applies to all of them. And while everything includes some strange examples, it doesn't generalize too far past what we need to do these kinds of higher category constructions. And so we see that this recovers the free category monad on graphs that I wrote before. And we get that a familial monad is one whose functor part is a familial functor, and where the unit and multiplication transformations are Cartesian. So in the interest of time, I won't get too far into what that means, but essentially it means that you have an operation whose arity is the representable graph. So in this case, it means that we have like a vertex operation that gives you the vertices you have before, and an edge operation that gives you the edges you have before. And the multiplication means that we can sort of nest these compositions, that these arity diagrams are composable in a meaningful sense. So for categories, we get these Lagrange paths and concatenation of paths. And you can think of that as parenthesizing these diagrams into subpaths and then concatenating them all. And then I'll just quickly mention that, not related to familial monads, but for familial functors, a zero set, where zero is the empty category, is just the one object category. There's only one functor from the empty category into set. And so a familial functor from zero sets into D sets just picks out a single D set. And later on, we're going to see that that's actually very helpful for giving a diagrammatic description of some of what we want to do. So keeping this example of categories in mind and on screen, we can start using different notation for these that makes it a little bit more tractable. We don't have to keep writing all of these HOMs everywhere. And we can sort of we can use these standardized names that we've assigned to the operations and the arities. And so this starts to look like how we work with polynomial functors, where polynomial functors are themselves disjoint unions of representables, in that case, endofunctors from set to set. And we write so for fc a polynomial, we write fc of 1 precisely because it is what you get when you apply that polynomial function or functor to 1, the singleton set. And then we get that these arities defined using these brackets, so fc bracket n, give you exponents for your polynomial. So this is just rewriting the representable functor notation from before using something that looks more like polynomials and indicates that this is something we're going to be able to work with using the tools of polynomial functors. And one thing to keep in mind is that fc of n, for instance, is a graph. And in polynomial functors, it's meant to be a set. So that tells you that we're going to need to upgrade our structure of the polynomial functors in order to make this kind of notation rigorous. And so that's exactly what we're going to do. So polynomial functors are just the subcategory of endofunctors on set, given by disjoint unions of representable functors. And these are closed under composition. They include the identity, and they give us this nice category theory that Topos Institute has worked on so diligently. And we've got a few standard results that have come out over the last several years regarding these polynomial functors and transformations between them, where the comonads with respect to composition, so polynomial comonads, are precisely categories. And I'm going to mostly black box this for today, though it's of course really interesting. But what this is doing is getting us closer to being able to talk about these familial monads that I defined without any reference to poly in the language of poly. So these composition comonoids are going to be our categories of cell shapes. So that's like C and D. And then given a monoidal category with comonoids and two comonoids in it, namely C and D, we can talk about a bi-co-module. So again, in the interest of time, I'm not looking to delve too deep into the structure and axioms of a bi-co-module, but if you know what a bimodule is for two monoids, which is more familiar from algebra, then this is really the meaningful dual notion for comonoids. All of the maps point in the opposite directions, and it satisfies similar equations where you have So P would be a polynomial functor with a left coaction by this comonoid C and a right coaction by this comonoid D. But the reason I don't really have to tell you so much about what those means is because Richard Garner showed that these bicomodules actually agree with familial functors. So if you have a bicomodule from the polynomial comonoids corresponding to the categories C and D, that gives you exactly the same information that we defined above for familial functors from D sets to C sets. And so we can do all of this in that sense in polynomial functors. We can build up this bicategory of categories and bicomodules between them and transformations and use them to talk about familial functors. And we can also use them to talk about D sets themselves. So I mentioned before, a familial functor from 0 sets to D sets is just a D set. And so among polynomial comonoids and bicomodules, we could write that as this bicomodule, which we denote using these sort of fancy arrows, from 0 to D. And this is going to help us with the diagrams. And in particular, bicomodules compose, and applying P as a familial functor to X as a D set is the same as composing these two bicomodules at the comonoid D. So we can give a name to this bicategory that I mentioned. We call it Cash-sharp, hence the title. And it's often regarded as a double category, but I'm not going to need the vertical direction today. And we call it Cash-sharp because, of course, it is a bicategory whose objects are categories, except now the one cells are these prafunctors. So prafunctors, PRA stands for parametric right adjoint, and people like that it sounds like profunctors when you write it this way. To distinguish, I would say that like a profunctor from D to C as just categories would be a familial functor or a like parametric right adjoint functor from D set to C set. So I wanted to introduce all these different notations, and I give them some meaningful semantic distinction. So if it goes from D to C, it's a bicomodule or a profunctor. Equivalently, if it's acting on the categories of D sets, then I would call it familial. But there are different conventions on this. And so then these familial monads we talked about are the among the formal monads in this bicategory. So we have this endomorphism in our bicategory from C to itself. It has a particular form, which comes right from the definitions, where for every different cell shape, which are the objects in C, we get a set of operations, the set T of 1 sub C. And for each of those operations, we have an arity diagram, which is a C set. And now, because this is a bicomodule, this notation makes sense. You expect to have a C set in the exponent here. And the Cartesian transformations that make it a monad are two cells in Cash-sharp. Not all two cells in Cash-sharp are Cartesian, but some of them are. And so we keep that adjective in place. Though, of course, some people will consider the bicategory where you only have Cartesian morphisms. But this one's nice because it comes from this standard construction of comonoids, bicomodules, and transformations in the category of polynomial functors. So that's the main idea, that we can port this definition into the language of polynomial functors. And so then the question is, what kind of results can we express using this language? And does this language make it easier to express any of these particular results? And so I'm going to tell you about one of my favorite ones. First, a refresher / crash course in nerves. So In category theory, it's fairly common to talk about the nerve of a category. So it's a functor, in particular, a fully faithful functor, from cat, the category of categories, to the category of simplicial sets, which is often written as a pre-sheaf category, but of course, if we use the simplex category op, then we get it as something of the form C sets. So the idea there is, if you haven't seen it before, that a category regarded as an algebraic structure can be turned into a geometric structure, where in a simplicial set, which is built up out of points and edges and triangles and tetrahedra and higher dimensional simplices, from a category, you send the vertices to vertices, the arrows to edges, and when you have two successive arrows that can compose, you send those to a triangle. So you make this picture I drew, which was sort of meant to look thin. You no longer regard it that way. You treat it as an actual honest triangle. And if you look at it from the right angle, you can see that this sequence of 3 successive edges can be regarded combinatorially as a tetrahedron. You've got, there's 4 different triangles in here, sort of this one, this one, this one, and this one. And if you think of that as a 3-dimensional shape, then that's sort of how we build this nerve as a simplicial set. And these are very popular for homotopy theory, which I won't get into, but is a big motivation for all this. And there are also nerves of lots of these different kinds of higher categories. And while some higher categories, like 2 categories, have many different nerve constructions, I am going to use what I call the standard ones. And we're going to see later on that that's actually something we can define rigorously. So for 2 categories, we send them to what are called Theta 2 sets, which are cell diagrams whose cells are, just like simplicial sets, can be regarded as diagrams over these sequences of arrows with the composites added in and with sort of higher dimensional information plugged in for those algebraic relations. You can do the same for 2 categories and get this category whose objects are these pacing diagrams. And where we think of these pacing diagrams as actually quite high dimensional objects, where you have like a triangle for each sequence of arrows. And the 2 cells are 2-dimensional. This column alone would be like a suspended triangle. And so these become very high dimensional, but ultimately we can just regard them sort of more diagrammatically as having, as the category with objects, these pacing diagrams and morphisms, which I'll get to in a minute, talking about how you can include these and what kinds of composition operations you have between them. So more on that in a second. Continuing our list of nerves, double categories have a nerve in bisimplicial sets, whose objects look like grids, and in fact composable grids, because just like in simplicial sets, you have this sort of long edge of the triangle, which corresponds to the composite of 2 arrows. In a grid, you have sort of these long subgrids. So any subgrid of this would give you a map from the single square into the grid, which hints at how we use these to model composition structure. And then finally, I'll mention for multi-categories, there's a category gamma, omega, whose objects are trees, like so, also with composability baked into their morphisms. And these are called dendroidal sets, and this nerve has been studied extensively as well. So let's keep this picture in mind of our arity diagrams that we're going to compose and using those to turn an algebraic structure into something more combinatorial. And we've got our definition of a familial monad written out as a polynomial. We've got our operations, we've got our arities, and we know that they behave nicely with the structure of a monad. And so Mark Weber proved in 2007 that for any familial monad of this form, you always have a fully faithful functor into some category of functors to set. In particular, using this category Theta T op, where the op is to follow our convention about using covariant functors. And so what is this category? We're going to build it out of our monad T. And in particular, its objects are just the operations in T, like I mentioned before, for each of the examples above. So all of our operations correspond to these different types of diagrams we can compose. Those are our objects. And then the morphisms, which are really how we treat these as arity diagrams, which are composable. The morphisms come from this kind of messy formula, but if we look into it, it's saying that it is morphisms of T algebras from the free T algebra generated by these arity diagrams. So it's the full subcategory of T algebras spanned by the free T algebras on these arities. So that certainly includes just like, inclusions of these arity diagrams as, in this case, two graphs, in this case, what I like to call multigraphs. But we also have other kinds of maps called co-compositions. So what you get there is when we regard this, when we take the free two category on one of these pasting diagrams and we insert all of these composite two cells, in particular in this one, we compose these two vertical cells and these two vertical cells, and horizontally compose those to get a big composite two cell. That's a single two cell, and we can include from the free two category on a single two cell into that. And that relates to this composition. And so that's in the category theta, which means that in theta op, for theta op sets, for every diagram of this form, we can compose it into a two cell. And so the structure of this category is going to tell us about the kind of composites we need to do, but treating them as structure maps or as the morphisms that make up this functor from theta T op to set, rather than algebraic structure coming from being a monad algebra. And so the picture looks like this, where for categories, if you have the free category generated by three morphisms, then you can map from the walking arrow into that long composite. And if you have this free two category generated by this pasting diagram, like I've described, you get a big composite of it that you can include this walking two cell into. And this falls for free out of the formalism. And so these are really the building blocks of this category theta T. We know that we have inclusions between these pasting diagrams, which then correspond to restricting them. If you have a diagram like this, you can always sort of cut out the bottom bit, and then you have a diagram that looks like this one above. But you can also always compose. And so if you have a diagram like this, you can compose it into a single two cell. And the op is how we go in that correct direction. So how are we going to do this in poly? What we're going to do is use a particular construction of both a polynomial, but in this case, I'm going to do it by comodules, called the what's called the right coclosure, right? Yeah, right coclosure of polynomials or bicomodules. So what that means is that for any pair of bicomodules, P and Q, like so, we get that we have a initial choice of bicomodule from D to C, equipped with a natural transformation from P to the composite of this with Q. So we have this particular definition of Q over P as taking something that looks just like P, but then applying Q to its arities. And that gives you, if the arities of P were E sets, applying Q to them gives you D sets, exactly what we expect. And the universal property of this is precisely that of a left con extension. So we have left con extensions in this bicategory Cash-Sharp. And this is the formula that we have for them. And this may seem kind of random. It certainly gives you something of the right type. But what we see is that this actually gives us a way of constructing the category theta T from our monad in Cash-Sharp. And so whereas previous, for instance, how Weber defined it was just sort of looking at it and seeing, okay, this agrees with the nerves that we already like, and it's a general construction, but it doesn't come equipped with any sort of universal property. Whereas Cash-Sharp gives us the ability to characterize this in a more universal way. So how's that going to work? Well, we can plug in T and T composed T for these two bicomodules. So now all of our categories are C, our bicomodules are T and T composed with T. And we get this still rather opaque looking formula for this bicomodule. In particular, it has as its positions, we would call them, or its operations, just the same ones as T. And now its arities are these like, T of the arities of T. And so we're going to see how we can go from there to something which relates to the morphisms in our category theta T. So making a little bit more room. If we work out exactly what this set, T of T bracket T, T bracket I, is, supplying our definition of T, we only need to unwrap that definition once on the outside. So we get that for every object, for every cell shape in our category C, and every operation, I should say T, not P, I'm sorry. Every operation of T outputting a C cell, we plug in T of T bracket I for Y, and we get homomorphisms of C sets from T bracket J to T of T bracket I. And then we can use the standard adjunction of coming from monad theory and the adjunction between T algebras and C sets to get that this is precisely the set of algebra maps from the free T algebra on T bracket J to the free T algebra on T bracket I. And that's particularly the set of morphisms in theta T op from I to J. We defined theta T as the full subcategory of T algebras on the free ones generated by the arities. And here we're seeing that this set, T of T bracket I, is the disjoint union over J of these Hom sets in theta T op. And this gets exactly at how we treat comonads as categories. So it gets a little bit complicated here because as defined, this T composed T over T is a bicomodule. But of course it has an underlying polynomial. If we just forget that this sum is sort of separated over C.
Right, Brandon,
and yeah,
the thing, you have a T triangle T over T in the top line in one line and a T triangle T in the other.
Oh, I'm so sorry.
Those two are the same, right?
Yeah, that's a typo, and it's the first one.
The two things I'm saying? Yeah, that one and the other
Oh
one.
God, it's like that in two places. I am so sorry.
Yeah.
So I'm gonna highlight to the extent that I am able to the correct one. Yeah, this is what happens when I get confused about the order of arguments in LaTeX functions. This is the right one. T trie T over T. And so it should say that in all three of these places. And I sincerely hope that it's right going forward. Very sorry about that. Right. And so without getting into too much technicalities, we can show that just from a complete abstract nonsense and the universal property of this left Kahn extension, that its underlying polynomial is a comonoid. And the category corresponding to that comonoid is theta T op. And it's precisely because of this fact that the exponents in this polynomial are a disjoint union over the objects in theta T op of the Hom sets in theta T op out of I. So how are we going to use this fact? So keep our definition of theta T, keep our definition, yes, thankfully it's written the right way here, of our left Kahn extension polynomial. And now we can just completely diagrammatically construct the nerve of a T algebra. So first of all, what is a T algebra? How are we going to write that? So I said before that a bicomodule from 0 to C is a C set, and that composing that bicomodule with T gives you the application of T to that C set. So in particular, T composed with A in cat sharp is T of A as a C set. And so a T algebra is exactly just a transformation from T composed A to A. Just like classically, we would describe it as a morphism from T of A to A. And then given that, to get this nerve, we can construct this diagram where on the right, we've got this algebra structure, T compose A mapping to A. And then on the left, we just have exactly the universal two-cell that defines this left Kahn extension. And I see it's no longer on the screen, but this two-cell on the right here, if we expand T compose T, we get these two copies of T, then the left Kahn extension, T up above. And what we see is that TA, T composed A, can be regarded as a coalgebra for the comonoid theta T op, as written here. And coalgebras for this regarded as a bicomodule correspond to theta T op sets when we treat this as a category. And you can show that by abstract nonsense in cat sharp. And so the construction of the nerve just reduces to this picture. And if we think about what T compose A is, it has a cell, just from the definition of our monad T, we have a cell for every instance of each arity diagram in A. And that's exactly what our nerve is. It constructs this cell diagram out of all of the different instances of the arities in A, regarded geometrically. And so that's all I have time to talk about today. I'll quickly mention there are also other uses of the cat-sharp formalism in higher category theory. We can get interesting functors between algebra categories and many other things, which are either in the reference or in a forthcoming blog post. But yeah, thank you so much for having me. It's really nice to be able to talk about this stuff from my time at Topos in my favorite online colloquium. So thanks so much. Here are the references.
Thank you, Brandon. Thank you so much. Thank you for that very illuminating talk, and so nice to see all these concepts being expressed in terms of polynomial functors and catch sharp. Those proofs were also very beautiful. Thank you. So I think we have time for a few questions. I know Brendan, he has to leave quite soon after this, so maybe we can take one or two questions from the audience. So feel free to either ask your questions in the meeting chat and I can ask them on your behalf, or you can raise your hand and I will call on you. So I see that we have two raised hands. So Kevin, how about you go ahead first?
Okay, thanks a lot, Brandon. Let me know if you can't hear me okay. Can you just go back one slide? I want to ask a really naive question just to have made it to your last slide here. Why does this theorem you've stated type check? So this is, you have drawn a map of C sets, basically, right? Why is that a nerve?
Yeah,
yeah.
so I realized that another diagram would probably be helpful here. But basically, what this uses is the fact that we can treat this left con extension as simultaneously a bicomodule in poly, but also as a comonaid. And I mean, it's a comonad in cat sharp. And there's sort of an abstract nonsense argument that I didn't have time to get to here that basically says that if you have a co-algebra for this, so just like an algebra is a map from T composed A to A, TA is a co-algebra for this because we have a map from TA to this composed TA. So the map is going the other direction, and this is a comonaid. If you have that, then TA as a polynomial rather than a bicomodule is a forms a bicomodule from 0 to this, regarded as a category.
Yes.
I hope that.
Okay. Yeah, I think you already probably said like exactly that, but thank you for saying it twice. Yeah, that helps.
Yeah, well, considering I neglected to write it,
yeah.
I appreciate the question.
Just a bunch of things that are the same as different sounding things to shift between. Thank you.
Thank you.
Well, thank you, Kevin and Brendan. David, I saw that your hand was up. Do you still have a question, David Spivak?
Maybe. Brandon, in Weber's result, the nerve result, do you know where or whether he used Cartesianness to get that fully faithfulness?
Oh, I should know the answer to this.
Do you expect that that's very important? Because I don't think we use it here, right? This would have worked even if T was not Cartesian.
Right. So one thing that we have not been able to do in poly is show sort of using the language of cat sharp that this nerve is fully faithful. And I will very tacitly say that I believe Cartesianness is necessary for that, because that gets into the idea that like these sort of iterated operations give you arities that are co-limits, and that wraps up into at least one version of the proof of Weber's result. He proves it using some pretty abstract two-category theory. So my expectation is, like you observed, if your monad is not Cartesian, you should still get I believe you should still get a nerve construction like this.
Right here, yeah.
I don't think anything we've done relies on Cartesianness, but it won't be fully faithful necessarily. I don't think there's any reason to expect that. So,
okay, thanks.
Still useful.
Thanks, David. Thanks, Brendan.
And if there are more questions, I can stay on in a few minutes.
Yeah, there's a question in the chat from M. I'm not sure if you'll be able to answer this, but I'll ask. Can you say a word about poly-TT, which I think is type theory, polynomial type theory. This is some work that David and others are working on. Poly-TT uses what formalism to express categories, comonads and poly or algebras for the graph monoid or a monad over linear comonads. And does poly-TT implement higher categories as well?
Yeah, I love this question. Because even while I don't really know much about poly-TT, so I'm not going to directly answer the question. I'm going to answer an adjacent question that I think is relevant, which is that all of these different ways of model. So I don't know poly-TT or how that works, but I will say that one of the motivations of doing these things in the language of polynomials is that it means that if you had an implementation of polynomial functors, which perhaps poly-TT is meant to be, then you start to be able to express in your natural language, or in your, I don't know, native language of a type theory or something, these constructions. And so that gives you a really easy way of, doing higher category theory, maybe even doing homotopy theory, which uses these nerve constructions heavily, in your computational language. And with regard to the other part of your question, the categories are polynomial comonads and algebras for a monad on graph, and also monads in the category of spans. And one thing that we do in this paper, all concepts are cache-sharp, which is the main reference for the nerve result I talked about today as well, is we also at least initiate the discussion of how we would compare these different constructions of categories, how they all live together. Because all three of those you find in cache-sharp. Familial monad algebras are in cache-sharp. So algebras on graphs are in there. Polynomial comonads are the objects of cache-sharp. Monads in the category of spans can also be found in cache-sharp between discrete categories. So we get all of these in cache-sharp, and we have some ways of mediating between them, which would hopefully make it easy to pick whichever one is most convenient computationally. But I don't know how it's been done before.
That's great. That's really good to hear. So David has a comment. He says that poly-TT is a two-level type theory for polynomial functors. You should be able to implement all three formalisms for categories in poly-TT. So I know you're rushed for time. I just have one quick question.
Yeah.
Quick question. You mentioned some applications in your abstract about database theory, effects handlers, and open dynamical systems. Can you say a one-liner or something about how higher categories apply to some of these applications?
Yeah, so the connection there is that those are other applications of cache-sharp. And you can find all of them in this first paper. So those are all things that we can do in cache-sharp. And the fact that we could also do some amount of higher category theory in the same language suggests that this is, both a good language for both pure and applied math. If you can do higher category theory, you're looking pretty good on the math front, I think. And databases and dynamics and effects handlers are a pretty wide selection of applications. And so what motivated our name for this paper, sort of grandiose all concepts reference, was that sort of all of these different things that we had seen in poly, databases, dynamics, effects handlers, higher categories, also generalized polynomial categories. All of these can just live inside cache-sharp in one place or another. And so it really provides a seemingly universal setting for a lot of the things that we've been working on at Topos.
That's awesome. That's a very sharp cat right there. Okay, I think this is all we have time for. Let's thank Brandon again for really great talk, and thank you for answering our questions. And Brandon, you'll be sharing our slides with us, I hope. And I think
so I'll fix the typos before I do.
Oh, thank you. And we'll post it on the Colloquium website. So if you need the details, please check out his paper as well as the slides. Thanks again. And yeah, I'm gonna end the live stream now. And so.
All right, thanks so much.
Great. I know you have to